Hey, welcome back. So today we're going to tackle one of the biggest, thorniest problems in AI right now. How do you train these enormous models that are literally changing our world without the whole thing grinding to a halt in a massive digital traffic jam? It's a really cool problem, and the solution is, well, it's seriously clever. Let's get right into it.
Really think about that for a second. You've got an AI model with, billions, maybe even trillions of connections? How in the world do you get all of those tiny little parts to learn together in harmony instead of just creating, complete digital chaos?
Yeah, that whole coordination mess, that's what we're calling the AI traffic jam. Because it turns out you can't just throw more powerful computers at it and hope for the best. In fact, doing that can make things way, way worse.
So just to give you an idea of the scale we're talking about, picture a symphony orchestra. But instead of 100 musicians, you have thousands of them. And each musician is one of those super powerful processors, a GPU. Now, for the AI to learn anything, every single one of those GPUs has to play its part at the exact same time, perfectly in sync with everyone else. It's a huge undertaking.
And that process of keeping everyone on the exact same page, that's called synchronization. You can literally think of it as every single GPU constantly shouting its latest updates to every other GPU in the system. They all have to agree on what the model looks like before they can take the next step. And, well, this is where our traffic jam really starts to build up.
Right. All that shouting, it just creates this massive communication bottleneck. The network, connecting all these processors, gets totally clogged with data. It's like trying to force a tidal wave through a tiny garden hose. And here's the kicker. The bigger and more powerful the AI model gets, the bigger that tidal wave of data becomes.
Okay, but let's dig into that a little more. What makes this synchronization problem so hard to solve? Why is everyone talking at once such a complete disaster for training these things efficiently?
This quote from the research paper we're looking at today it hits the nail on the head. It says the amount of data that needs to be synced up grows right alongside the model size. So think about that. If you double the size of your AI, you literally double the size of your communication headache. This has been the fundamental roadblock, the thing that's been holding us back from building even bigger and better models faster. But what if there's a totally different way to look at this? Some researchers had this brilliant insight. Maybe not all of that information being shared is equally urgent. Maybe, just maybe, some updates are way more important to share right now than others. And this, right here, is the core idea. The researchers figured out that you can basically split all these updates into two different buckets. In one bucket, you've got the fast components. Think of this as the breaking news. It's stuff that changes really fast, but in a predictable way. The technical term is high spatial autocorrelation, which is just a fancy way of saying the updates are pretty similar across all the different processors at any given moment. Then, in the other bucket, you have the slow components. These are the long-term trends. They evolve more slowly, but they're absolutely crucial for the model to actually learn. The key is, they don't need to be broadcast every single millisecond.
So that leads to this total game-changing question, right? What if you could build a system that was smart enough to know the difference? A system that only syncs up that urgent, breaking news stuff instantly and lets the long-term trends just kind of catch up later.
Well, that is exactly what this new algorithm does. It's called DeMo, which stands for Decoupled Momentum Optimization, and it's a completely fresh take on how to manage this insane communications flow.
This whole approach comes from a paper by Bowen Peng, Jeffrey Quesnel, and Diederik P. Kingma. And their work introduces this really clever new optimizer that just attacks the communication bottleneck head-on, simply by being smarter about what data it chooses to send and when.
The real beauty of DemoS is how simple the idea is. It basically acts like a smart traffic controller. So it watches all the updates happening, and it intelligently separates the fast, breaking news from the slow, long-term trends. Then, and this is the key, it only broadcasts the fast stuff immediately to everyone. The slow stuff, it gets held back, updated locally on each processor, and then synced up way less often. Such a simple concept, but the impact is, well, it's profound.
Okay, so the million-dollar question, does it actually work? Did DeMo really manage to clear up that digital traffic jam we've been talking about? Let me tell you, the results are, frankly, they're stunning.
All right, let's just look at the proof right here. These charts show the training progress, right? The goal is to get that loss value as low as you can. That red line, that's the standard way of doing things, an optimizer called AtomW. Now look at those other colorful lines. That's Demo. And you can see plain as day, Demo doesn't just keep up, it consistently gets a better result, a lower loss in the exact same amount of training time. It's not just faster, it's better.
But here it is, this is the headline number. By being so smart and selective about what it synchronizes, Demo cuts down the communication traffic by over 98%. Nope, that is not a typo. It pretty much eliminates the traffic jam. Just gone.
And this table just lays it all out crystal clear. The standard optimizer Atom W, it gets to a final loss of 2.77, but look at that communication cost, over 2,400 megabytes for every single step. Now look at Demo. It gets a better final loss, 2.65, while using less than 28 megabytes per step. I mean, come on, it's better performance for a tiny, tiny fraction of the communication cost. So what's the bottom line here? What should you really take away from all this? First, Tomorrow is a genuine breakthrough. It basically solves one of the biggest scaling problems in AI. It means we can train massive models way more efficiently, even if we don't have the best, most expensive networking hardware. And maybe the best part of all, it's designed to be a drop-in replacement, so developers can start using it right away without having to tear down and rebuild their entire systems. It's a huge deal. And that really leaves us with one final, super exciting thought. For years, this communication bottleneck, this traffic jam, has been a major roadblock holding things back. So now that the road is clear, what new, even bigger, even more capable AI models are just waiting for us around the corner? The possibilities? Well, they're pretty incredible to think about.